这可以凹吗？还是不行？把它凹坏。等一下，好。我早上我遇到那个谁，荷兰狗，我遇到他，他有讲一下，就是说他跟我失业了，就也是本来想，就你明天会上去哪里？
我等一下就要上去。对啊。
哦，是吃饭这样子还是？
没有，你等一下一起吃饭，我跟你吃完饭再上去。
哦，没关系啊，没关系啊，就我跟朋友还有约。
你跟朋友还有约？
他们现在在课上班。
哦，好，所以你要跟你朋友吃饭这样。
哎呀，很久不见了。等下再跟你聊。
啊？
等下再跟你聊。
好。
结束会在这边吗？会？你会马上赶回去吗？
没有，我晚上会跟我朋友。
OK，好。那等一下我们聊一下。
好。OK。喂。
好，那我们今天
喂。
中央研究院的吴侊儒博士来我们演讲。他今天要讲的是 Capacitive Curvature Finsler Matrix and Vector Bundle。
OK。谢谢廖教授的这个邀请，然后也是很高兴，大概10年了吧，毕业大概10年了吧。我之前是那个理学院学士班的，11级的，然后很高兴可以回来。我想，因为有很多单字都是英文的，所以我用英文讲可能会比较那个一点啊，所以没关系，就避免在那边中英文夹杂，我就全部用英文讲好，会比较顺一点点。好，然后 So I will talk about my recent paper on positively curved Finster Matrix on vector bundles. And we'll begin with X is a complex manifold of dimension n. And we start with a line bundle L over X. So L is a holomorphic line bundle. So there are two concepts about positivity for this line bundle. So one is in the sense of differential geometry. The other is in the sense of algebraic geometry. Okay. So L is said to be, so this line bundle L is said to be positive if there exists a Hermitian metric H on L such that its curvature so its curvature theta. So by definition, curvature of a Hermitian metric on a line bundle by definition is negative I d bar log h. And if you want to write it out in terms of local coordinates, it's negative I log h z alpha z beta bar, dz alpha, which dz beta bar, summation over alpha and beta. So it's a 1-1 form. If you write out the curvature form in terms of local coordinates, so it's this thing. So if this curvature is positive, okay. So if the curvature of this Hermitian matrix is positive, then we say L is positive. So this is definition. On the other hand, L is said to be ample if there exists a positive integer k such that the following map is well defined and an embedding. So this map goes from the manifold X to the projective space of so H0. So this is space of holomorphic sections. So you have to take so you have this space of global holomorphic sections, and you consider its dual space. So this is a vector space. And for vector space, you can consider its projective space. It's a projective manifold, projective space. And it maps a point in this manifold to the set of all the holomorphic sections. Vanishing at X. So given a point, I consider those sections vanishing at this point. So if this map is well defined and is embedding, we call L ample line bundle. Okay, so this definition is purely differential geometry. This is purely algebraic geometry. It turns out they are equivalent. Okay, so these two concepts, they are actually equivalent. And one direction, so this direction is somewhat easy. This is almost by definition. But the other direction is Kodara's embedding theorem. So this direction is almost by definition. This direction is the Kodara's embedding. Okay. So this is for line bundles. So vector bundle of rank 1. And people have been trying to extend this equivalence to vector bundles higher rank. So we'll move on to a holomorphic vector bundle of rank over X. Okay, so the previous case, we're considering R equal to 1. Now we're considering higher rank bundles. Okay, and we can try to formulate a conjecture similar to this and try to prove it. Okay, so before making a statement or a conjecture, we need to define positivity and the endpoints for vector bundles. Okay. So the positivity for vector bundles, I will use Griffith positivity. Is Griffith positive? So what do I mean by is Griffith positive? So a vector bundle is said to be Griffith positive if there exists a Hermitian metric H on E such that its curvature theta. I will always use theta to denote the curvature. So curvature of a Hermitian metric over a line over a vector bundle. This is actually a 1-1 form. It's a 1-1 form with values in endomorphism of E. Okay, I'll explain this sentence later. Okay, such that this curvature satisfies okay, so for every U in E, for every non-zero vector, I can consider the inner product of theta U with U. And this is a 1-1 form. So I require this 1-1 form to be positive, okay, non-zero. So if this vector bundle carries a Hermitian metric such that its curvature has this positivity property, then we say E is Griffith positive. Okay, so if we write out everything in terms of local coordinates, theta, so in terms of local coordinates, theta can be written as summation theta alpha beta bar dz alpha, which dz beta bar. Okay. Where this coefficient, this is the endomorphism. This is the endomorphism of E. Okay, so it's a 1-1 form with coefficients with values in endomorphism. So that's what I mean earlier here. Okay, so curvature. So curvature of a metric on a vector bundle, if you write it out in terms of local coordinates, it's such a thing. And this theta U inner product with U becomes locally theta alpha beta bar. So this is endomorphism. I use this endomorphism to act on a vector that gives me another vector, and I take inner product of this with this vector U with respect to the Hermitian metric. So this is a number, and we can consider this 1-1 form. Okay, so this inner product of theta U with U in terms of local coordinates, such a thing, and we want this to be positive. If this is positive, then we say E is Griffith positive. So this is positivity for vector bundles of higher rank. And when I is 1, it goes back to this positivity for line bundles. So endpoints, we have to define endpoints for vector bundles E. and this definition is going to be quite involved. Okay, so how are we going to define emptiness for a vector bundle? We look at dual bundle first. Okay, and we consider its projectilization. Okay, so what do I mean by the projectilization of a vector bundle? So it's the following. So for each point z in X, we have a fiber which is a vector space. Okay, so this is a vector space. And we can consider the projective space of this vector space. Okay, so it's a projective space of vector space. So it's a projective space. And right, for each z, we have this projective space, and we simply consider the collection of all these projective spaces, and that collection gives you P star. Okay. A picture I always keep in mind is the following. If this is my manifold X, and this is my bundle E star, say. So for each point z, I have this fiber, which is a vector space, and I can consider this projective space. So it's like a circle. So projective space of a vector space is like a circle. So I have a family of circles. It's something like a tube. So this is PE star. Okay, P star over X. Okay, so this picture might help you to see. And over this projectivized bundle, there's a line bundle called tautological line bundle. Tautological line bundle over PE star. Okay, and it's usually denoted by O -1 PE star. And this construction is this. So, so for each point in P star, it's a one-dimensional space in E star, right? So projective space. So maybe let me remind you. So if I have a vector space, so V is a vector space, and PV, the projective space V is a collection of all those straight lines, all those one-dimensional subspaces. Okay, so this is the collection of all those one-dimensional subspaces in V. So a point in PE star is a straight line in E star. So given a point in PE star, I automatically have a straight line. Okay, I use this straight line as my fiber. That gives me a line bundle, and that's the tautological line bundle. So for each point, there's a straight line. For each point, there's a straight line, and that's my line bundle. It's tautological, and its dual is denoted by O1 PE star. Okay, so if this line bundle is ample, then E is said to be ample. Okay, so in order to define ampleness for vector bundle, we look at its dual, and we consider its projectivization. We consider its tautological line bundle, and we take another dual. If this line bundle is ample, then E is said to be ample. Because we already know how to define ampleness for line bundles, so this sentence makes sense, and this definition makes sense. Everything is well defined. Okay, so if this is the first time you see the definitions of Griffith positivity and ampleness, it's a little bit overwhelming. So now we have ampleness and positivity for vector bundles. Natural question to ask is, are they equivalent? Okay. It turns out one direction is true. If E is Griffith positive, then it is indeed ample. So this is known. It's proved by curvature, a direct curvature computation. Or you can use the fact. So Griffith negativity is equivalent to log of the length of S. This is strongly pre-subharmonic for every holomorphic section, non-vanishing holomorphic section. Okay. You can use either direct curvature computation to prove this statement, or this characterization of Griffith negativity to prove this statement. Okay, so one is differential geometry, the other is several complex variables. Okay, maybe I should mention a very important fact. Okay, maybe later. Okay, so one direction is known. How about the other direction? Okay, so how about the other direction? So the other direction, whether ampleness of E implies Griffith positivity. This is a conjecture by Griffith. It's Griffith conjecture. Okay, it's made in late 60s, and it is still open. So if a vector bundle is ample in the sense of algebraic geometry, can we find such a Hermitian metric with positive curvature? So this is unknown. This is open. Except it's true. It's true when the dimension of the underlying manifold is 1. Okay, so if the manifold is of dimension 1, if the manifold is a Riemann surface, then this conjecture is true. Proved by Uemura, 1973, and later by Campana, the Flanner, 1990. Okay, so very little is known about this conjecture. It's still very open. Not much is known. So a few years after Griffith made his conjecture, Kobayashi proposed using Finster Matrix instead of a Hermitian matrix to study this equivalence. So we have to introduce Finster Matrix. So Kobayashi 1975. He said, why don't we use Finster Matrix? Okay, Finster Matrix. So remember, so Hermitian metric, a Hermitian metric is a collection of inner products. So each fiber is an inner product. Each fiber is an inner product. Finster metric is a collection of norms. It's a collection of norms without triangle inequality. Triangle inequality. So to each fiber, I assign a norm, but it doesn't satisfy triangle inequality. And this collection is called a Finster metric. So it's much weaker. Instead of inner product, we're considering a norm, but without triangle inequality. Okay, so this is a Finster metric. And for a Finster metric F, so F is strongly pseudo-convex. So a Finster metric is said to be strongly pseudo-convex if the fiber-wise complexation of F is positive. Okay, so we can compute this complex hessian, this second derivative as a matrix. Matrix is positive. Then we say F is strongly pseudo-convex. It has some concavity. Okay, and for this kind of Finster metric, we can define curvature, Kobayashi curvature, curvature. Okay, it's a 1-1 form on the projectivized bundle of E. Okay, so I don't want to go into details on how to define this curvature 1-1 form. Okay, what really matters it's the following lemma by Kobayashi in the same paper. So Kobayashi's lemma. So in the very same paper, he proved the following. Okay, so before stating this lemma, we need to observe this. So a Finsler metric F on E corresponds bijectively as a 1-to-1 correspondence to a Hermitian metric. HF on this tautological line bundle. Okay, so there's a 1-to-1 correspondence between Finster metric on a vector bundle and Hermitian metric on the tautological line bundle. So Kobayashi proved the following. So first, this Finster Matrix is strongly pseudo-convex. If and only if the corresponding Hermitian matrix is curvature. This curvature restricted to each fiber is negative. So for every z in X. Okay, so it's strongly pseudo-convex if and only if the curvature 1-1 form restricted to each fiber is negative. And 2, assume F is already strongly pseudo-convex. So once F is strongly pseudo-convex, we can talk about Kodaira curvature, right? Okay, we can define Kodaira curvature. And F is Kodaira positive if and only if this curvature, this 1-1 form, has signature n r-1. So number of positive eigenvalues is n, number of negative eigenvalues is r-1. Kodaira negative if and only if signature is m0, m plus 0, and m plus r-1. So all eigenvalues are negative. Okay, so it's a negative 1-1 form. And this lemma is extremely useful because everything you need to know about Finster Matrix can be derived from the corresponding Hermitian matrix. So all you need to care is the corresponding Hermitian matrix. Okay, so the curvature and the strong pseudo-convexity, everything is encoded in the curvature of this Hermitian matrix. Okay. And Kobayashi, he proved instead of, he proved the following. He showed that E is ample, so Kobayashi, 1975, he showed that E is ample if and only if the dual bundle is Kobayashi negative. Namely, the dual bundle carries a Finster matrix whose curvature is negative. Okay. And he asked, so he conjectured, this is Kobayashi conjecture. Kobayashi's conjecture. So he asked whether ampleness of E is equivalent to E being Kobayashi positive. Okay, so this is on the dual side. And he asked whether if E is ample, namely E is positive in the sense of algebraic geometry, can we find a Finster matrix on E that has positive curvature? Okay, so right, so this is known and this is unknown. And when facing this conjecture, the first difficulty is it's this. So there's a duality issue. Because if this is true, basically what we need to solve is whether a bundle is Kobayashi positive, if E is Kobayashi curvature, is the dual bundle Kobayashi negative, right? So there's a duality thing. So that's basically what we need to prove, or what the conjecture is about. So I remember in the Hermitian case, so I didn't mention this, but so this is an important fact. So in the Hermitian case, so in the Hermitian case, so a Hermitian metric is Griffith positive if and only if its dual Hermitian metric is Griffith negative. Okay, this is well known that you can compute this by hand. So if I have a Hermitian metric positive, then its dual is going to be negative. But in the Finsler case, we don't have such a duality. So if I have a Finsler metric, I can consider its dual Finsler metric. If this is positive, can we say this is negative? The answer is not. So this is wrong. Okay, there are counterexamples. So the duality doesn't work in the Finsler case. Otherwise, Kobayashi conjecture would have been solved long time ago. However, so Misi 1978 is a wonderful result. So this mathematician, so Misi 1978, he said if the Finster metric is in addition strongly convex, okay, not just pseudo-convex, but convex, okay, so if we have this extra assumption, then we do have duality. So this duality works. Okay, so if we know the Finster metric is strongly convex, not just pseudo-convex, then duality works. Okay, the dual Finster metric will have the opposite curvature. Okay, and how to obtain this convexity is a key point in my result. All right. So let's go back to Kobayashi conjecture. So Kobayashi's conjecture, one direction is solved recently, actually. So in Kobayashi's conjecture, actually one direction is known. This direction. So if if E is Kobayashi positive, then E is actually ample. Okay, this is recently by Feng, Liu, and Wan, 2018. Okay, so they show this direction is actually true. Okay, so if a bundle carries a Finster metric whose curvature is positive, then E is going to be ample. E is going to be positive in the sense of algebraic geometry. And their proof relies on Schiff-Kohl homology. They use a lot of Schiff-Kohl homology. And later, I will give you a proof that is different. It's more differential geometric. It's totally different from their proof. Okay, so maybe let me summarize the conjectures so far. So we have ampleness, and we have Griffith positivity. Finally, Kobayashi positivity. This is Griffith's conjecture. This is Kobayashi's conjecture. And this direction, if I have a Finster Matrix positive curvature, can we find a Hermitian metric whose curvature is positive? As far as I know, this direction is also open. So we have these 3 open questions. And in this paper of mine, I make some progress, some small result regarding this direction and this direction. Okay, so let me get into this very detailed technical construction. So so before I go into the proof, so each reversed arrow is true. Each reverse direction is true, as I mentioned earlier. So Griffith positivity implies ampleness. Kobayashi positivity implies ampleness. Griffith positivity implies Kobayashi positive. So each reverse direction is true. Okay. And for the rest 20 minutes or 15 minutes, I will try to deliver the main result, my paper. So I need to introduce this Hermitian matrix on direct image bundles. Hermitian matrix on direct image bundles. Okay. And we go back to this diagram. So I have a bundle and consider its projectilization. And we look at this O1, which is usually called the hyperplane line bundle. And so for a positive integer k and a point z in X, there's a canonical isomorphism. Canonical isomorphism. Phi kz goes from a symmetric power of E star to H0, space of holomorphic sections, global holomorphic sections of this fiber. Okay, so this will be very technical. So there's a canonical isomorphism from this symmetric power vector space to space of global homomorphic section. It's a canonical isomorphism. I don't want to go into the details. But what's important is if given a Hermitian metric H on O1 on this line bundle and a family of Hermitian metrics omega z on the fibers. So we know what it means by a Hermitian metric on line bundles. A line bundle of a Hermitian metric. So what do I mean by a family of Hermitian metrics on the fiber? So for each fiber, it's a projective space. So it's a manifold, and I assign a Hermitian metric omega z to this manifold. And it's parameterized by points by z in X. So it's a family. So for each slice, there's a Hermitian metric. So given this H and this family omega z, we are able to define a Hermitian metric on the direct image. So what's direct image? So we are able to define. So once we have these two data, once we have this H and this omega z, once we have these two data, we're able to define Hermitian metric. HK on the direct image, so on this vector bundle actually, on the symmetric power of E star. Okay. And so don't have too much time. So okay. Yeah, so let me at least tell you how to define this Hermitian metric. So so for two vectors in this bundle, I need to define the inner product of these two vectors, right? So in order to define Hermitian metric, I need to define I need to define the inner product of these two vectors u and v. So it's defined in a very natural way. Since u is already in this symmetric power, so we can apply this canonical isomorphism then I have a global homomorphic section. Two global homomorphic sections actually. One from U, the other from V. So I have two global homomorphic sections. Values in here. But there's already a Hermitian metric on O1. So there's a Hermitian metric HK on OK. So I can consider the inner product of these two global homomorphic sections. That gives you a global function on this fiber, on this projective space. So now I have a global function on this manifold. Meanwhile, omega z is a Hermitian metric, actually a Hermitian form. Once I raise to the top power, it gives me a volume form. So I can integrate this global function against the volume form over this manifold. That gives you a number. So that number is the inner product of U and V. So that's how we define this Hermitian metric on direct image. So that's Hermitian metrics on direct image bundles. Okay, so it's rather technical. So this formula has a lot of applications in algebraic geometry, complex geometry, Kähler geometry. And finally, so theorem says if this Hermitian metric HK, so this Hermitian metric, this special Hermitian metric is Griffith negative, then what? Then the bundle E star carries a Finster metric, convex Finster metric. strongly proof subharmonic on the total space. Okay, so we go from the symmetric power to the bundle itself. Okay, so this is actually not so easy because so it's easy for line bundles. So if I have a Hermitian metric on say LK, it is easy to get a Hermitian metric on L. You simply take kth root, then you have a Hermitian metric. But for vector bundle, you can still take kth root, but you will only get a Finster metric, not a Hermitian metric. Okay, because once you take kth root, it might not satisfy the some identity. Don't remember. Parallelogram law or something? Yeah. But anyway, it's not going to be a Hermitian metric. So this is somewhat non-trivial. Moreover, the bundle E itself. Okay, so here we're talking about the dual bundles. And the bundle itself is Kobayashi positive. And the Finster metric is convex. Okay, so that's one of the results. The proof is actually not very difficult. I think can deliver this proof in 5 minutes. So how are we going to prove this theorem? Well, as I said earlier, you just take kth root. So for a vector u in E star, we can define a Finster metric. We can define a Finster metric f of u by first raising u to a power k. So u is in E star. So uk is in the symmetric power of E star. Okay, but on this symmetric power, there's already a Hermitian metric hk. So I can measure its length and then take 2kth root. And this is readily a Finster metric. I can show this is Finster metric. And this Finster metric is going to be Kobayashi negative by Griffith negativity. Because HK is assumed to be Griffith negative, and the kth root of this can be shown to be Kobayashi negative. Moreover, F is convex. Okay, this is perhaps the punchline in the proof. Okay, it's by Minkowski. Very basic Minkowski's inequality. Okay, and the observation is rather simple because HK is defined in this way, so it's actually L2 norm. This is actually L2 norm. So if you take u equal to v, then you see this is actually L2 norm. So it's kth root or 2kth root. This is actually an L2k norm. So for L2k norm, of course, it satisfies this Minkowski's inequality. And from here, you can easily prove the convexity of F. Okay, just manipulate some inequalities and you will have convexity for F. So that's the first part of the theorem. So E star carries a Finster metric that is convex and Kobayashi negative. And for the second part, is also not difficult because we have this Finster Matrix, and I perturb this Finster Matrix by a small Hermitian matrix. So I have a new Finster matrix. And this new Finster matrix is going to be strongly convex. So the point of adding this small Hermitian matrix is to turn convexity to strong convexity. And it is still strongly pluri-subharmonic. So once we know it's strongly convex by the Mises result, its dual is going to be Kobayashi positive. And that's the second part of the proof. Okay, so I still have a lot, but don't have that much of time, so I'll stop here, and thank you for your attention. 大家等着吃饭。哦哈。可以有关系，可以有。我们最近在做，我跟我一个朋友最近在做。对，可是我不认为 quantization 可以去解那些 conjecture， 就是那些 conjecture 真的要硬碰硬，就是 quantization 应该没办法做 ，quantization 应该都是做一些 stability 的东西。因为 quantization 跟这个吗 ？quantization 跟这个的话，就是它可以就假如说一是E star 好了，假如说 E star 是 ample 的话，这个东西会是 positive。然后这上面的 Hermitian matrix 会对应到这上面的 Finsler matrix， 有一个 one-to-one correspondence。然后这个地方，假如说有 positive line bundle 的话，这里有一个很自然的 quantization。这很最近30几年 Cater geometry 都在做这种东西。然后你可以问说，就是我这个东西可以用一串很好的 Hermitian matrix 去逼它。那这每一个东西你都可以对应到一个 Finsler matrix。所以这很自然，它会逼过去。你可以问说，它的 curvature 啊会不会逼过去？然后它如果说它的 curvature 是 constant scale curvature 啊，或是之类的，它会不会逼过去？对，我们可以问这些问题。然后这个比较简单一点，然后另外比较难的是，如果说它 curvature 是 signature R 这个的，那这就比较难一点，这个我们就不知道了。它不是正的，然后很多东西都不知道。OK。
进了陈守庆了吗？
有，去找我刚
所以什么时候回来的？很久了啊，我都没有注意到。去年就回来了。因为我也要1年前 Lemper 来一次，那时候你还没毕业嘛，他还跟我说